Welcome back to the course entitled Symmetry, Stereochemistry and Applications. In the last week, we have discussed about the stereochemical aspects of various organic reactions involving the carbonyl group, and we have seen the reactions are sensitive to different stereochemistry of the carbonyl compound. So, in this week, we are trying to go through the new portion where we will try to highlight. We are going to highlight the stereochemical importance of chemical reactions and how the stereochemistry of a reaction can be predicted based on the nature of the substrate and the nature of the reagent, solvent, etc. So, this portion of stereochemistry is technically termed as dynamic stereochemistry, where we will try to understand the differences and the meaning of stereospecificity and stereoselectivity in organic reactions. So, dynamic stereochemistry deals with the chemical properties of molecules in relation to the stereochemistry of reactants and products of a reaction. So, depending on the substrate, reagent, and the solvent, the stereochemistry of the product is controlled. We have discussed this in a very brief manner in one of our earlier lecture, where we have discussed about the substitution reactions, elimination reactions, and then in some lecture where we talked about the addition reactions. You may remember that in case of SN1 reaction, we encounter racemization in case there is a chiral center associated in the substitution reaction. Whereas in case of SN2 reaction, we get to see that the configuration at the chiral center is inverted and umbrella inversion happens. Similarly, in case of elimination reaction, the products that are formed in E1 and E2 reaction may be different because the reaction mechanisms are different in case of E1 and E2. As a result, you end up getting two different products based on the reaction mechanism, whether it is E1 or E2. So in this lecture, in this couple of lectures in this week, we will discuss more about addition reactions and their corresponding stereochemical preferences. So, when we try to define the terms stereoselectivity and stereospecificity, these are used in the literature in some overlapping manner. So, we need to understand these two terms very clearly. So, when we have a substrate, suppose X, and the substrate gives in a reaction either a compound A1 or another compound A2, one of them in 100% abundance and the other isomer is not formed. So that reaction is called the stereospecific reaction. That means only one specific compound A1 or A2 is formed and the other one is not formed. The other type of chemical reaction can be considered where your substrate X gives one of the stereoisomer in excess compared to the other stereoisomer, which appears as a trace compound, and this type of reactions are called stereoselective reactions, which means this reaction procedure selects one among the two possible products as a preference and gives that particular product in excess, and the other product also forms in as a minor product or a trace compound. The third type of reaction is something which you have already encountered, is like SN1 reaction, where if you had started with a chiral substrate, SN1 reactions, you know that it goes through a carbocation formation, and once the carbocation is formed, then it is equally probable that the carbocation can be attacked by the nucleophile from the above and below and form two different isomers in same abundance. So in that case, A1 and A2 will form in 50% each ratio, so 1:1 ratio. So there will not be any stereochemical control or preference. So what we can see from this few lines, that a stereospecific reaction is essentially stereoselective. That means a stereospecific reaction yields only one particular stereoisomer between the two, and hence it can also be considered as a stereospecific reaction. But on the other hand, when you try to understand this stereoselective reaction, it is selective between the two particular compounds but not specific that which one will be major product or which one will be minor product, or it is not as specific that it will only form one of them. Therefore, this term, this concept can be summarized as all stereospecific reactions are 100% stereoselective, but the stereoselective reactions are not stereospecific. So when we try to understand the stereospecificity of a reaction, we can simply consider a particular reactant which is one of the two diastereomers, and we do a particular reaction and we get a particular product. And then if we choose a different diastereomer, then in the product of the same reaction we get a different diastereomer. So here it is stereospecific. A particular diastereomer, suppose diastereomer 1 gives you diastereomer medic product 1, and diastereomer 2 gives you diastereomeric product 2. We don't see any formation of any of these two cases that you start with a diastereomer 1 and get a product as diastereomeric product 2 even in a trace quantity. So we call it as a stereospecific reaction. On the other hand, the stereoselective reactions are such that where one particular reactant can yield two products, one of them is a major product, the other one is a minor or trace product. So it may be like one product is 80% and the other one is 20%. Then we call it as major and minor. Whereas in some reactions, it may be the case that one forms 98% and the other one is 2%. In that case, we would call it as a major and trace product. These stereoselective reactions can be divided into different groups or parts. One can think of substrate stereoselectivity, which means the reactant, which is the substrate, can be a mixture of two enantiomers or two diastereomers, and the reaction is such that the one of the two stereoisomers present in the reaction medium reacts and gives you the product. So that kind of selectivity is a selectivity on substrate. So one of the two substrates that are present in the reaction medium reacts to give you a product and the other substrate does not react. So that is called the substrate stereoselectivity, and normally that is observed in enzyme catalyzed reactions. The other possibility is that the product stereoselectivity. So in this case, a particular reactant may react with a particular reagent or solvent or a catalyst to produce two different products, and those two products are produced in two different quantities, and in that those two products that we are talking about can be either a pair of diastereomers or a pair of enantiomers. So, if the products are a pair of diastereomers, then that particular reaction is termed as diastereoselective reaction. Whereas if the products are a pair of enantiomers, then we call that as the enantioselective reaction. Let us try to see the stereospecificity and stereoselectivity in some common reactions. So let us start with the reactions with carbene. We have discussed in one of the previous lectures that the species the CH2 double dot is called an carbene or methylene carbene, and this methylene carbene can exist in two different forms, singlet and triplet. So these two different forms of this carbene are different in terms of their bonding. So this singlet carbene, the carbon is in sp2 hybridized state, and the two electrons, the lone pair of electrons reside in the sp2 hybridized orbital, and you have a vacant p orbital present in this singlet carbene. Whereas the triplet carbene exists as a sp hybridized carbon. So in that you have two vacant p orbitals. Each one of those contain one electron each. sp hybridization. So you see the two carbenes are structurally different, and as a result of the structural difference, these two carbenes react differently with the alkyl. So if we use a cis compound, rather cis-2-butene, using the singlet carbene, it forms the CH3 cis compound. So this we started as Z2-butene. We get here as cis-1,2 dimethyl cyclopropane. Similarly, if we start with the corresponding trans variety, that is the E2-butene, and do the same reaction with the singlet carbene, we would end up getting the corresponding trans dimethyl cyclopropane derivative. On the other hand, if we had done this reaction with the triplet carbene, we would have got a mixture of cis and the corresponding trans isomer. So from this observation, one can conclude that the reaction with the singlet carbene happens in a concerted mechanism. So that this happens through a cyclic intermediate and hence no change in stereochemistry of the methyl groups. But then, when the triplet carbene reacts, the reaction goes through a different mechanistic pathway, and in that case, it is believed that the reaction proceeds through the formation of a diradical which can undergo conformational changes to form two different products. So what happens is when the diradical forms, it is possible to have a rotation about the single CC bond, and the cis isomer also gets twisted through that CC single bond, and the ring closure happens. As a result, we get to see two different products, the cis and the trans isomer. So here it is clear that this reaction of alkene with a carbene gives you two types of reactions. One is a concerted step, which is also called a pericyclic reaction, and the other one proceeds through a diradical formation and results into two different products which form in equal quantities. Let us see one more example of the stereospecificity and selectivity in case of addition reaction to CC double bond. So let us take the example of a cyclohexanone derivative which contains a tertiary butyl group in the para position, in the 4th position with respect to the C double bond O, and as you know, the terbutyl group is more stable at the equatorial position compared to the axial position. So this compound, when treated with lithium aluminium hydride, what happens, you already have seen that the carbonyl groups gets reduced to form the alcohol. So the product is a cyclohexanol derivative, and what we see in this reaction that the OH with the equatorial position is the major product, while the other possibility that OH is in the axial position is the minor product. So here what we see is called the stereoselectivity. On the other hand, if we try to look at the elimination reaction offered by these two particular compounds that I am drawing, which is this one is a meso compound, when we treat this compound with iodide, what happens is bromine elimination happens and it produces the trans isomer of the double bond. But when we use a different substrate where the bromines are on opposite side, which means it is one of the two optically active forms of dibromobutane, in the same reaction, the elimination of bromine leads to the formation of the corresponding cis isomer, that is the Z2-butene. So these two reactions are called the stereospecific reaction, where we see the substrate specificity. So here it is possible to choose different substrate to get the target molecule made through these stereoselective or stereospecific synthesis routes. When we try to do reactions with the double bonds, what we have already seen is, I am going to repeat that again. If we start with a trans product and do a bromination reaction, we could end up making compounds where there won't be any stereochemical preference, both the isomers will be formed. So we don't see any specificity or selectivity. So we could say that it is no specificity or selectivity in these reactions. So here what we know is that the reaction proceeds through the formation of bromonium ion, which would look like this. And Br minus can equally attack on this or that carbon to give rise to products which are a pair of enantiomers. Therefore, these reactions do not have any stereospecific or stereoselective control, as we already have seen in our previous lectures. So from here we will continue in the next class.